In this video, what I'm going to do is I'm going to take you through a few different ways in which we can deal with heteroskedasticity in a basic ordinary least squares cross-sectional model. Now, as we previously discussed, the main issue with heteroskedasticity is that it causes us to lose precision, mainly with respect to the standard errors as estimated in order for statistical significance to be determined. Another particularly sticky issue, and certainly a worse version of heteroskedasticity, is one in which the heteroskedasticity is born out of some specific heterogeneity that we are not able to address or aren't addressing in our particular baseline model. And so there are different ways in which we sort of want to deal with heteroskedasticity depending upon the nature of how it actually is showing up in our regression. So what we're going to do is we're going to start with some basic ordinary least squares regression. We're then going to test for heteroskedasticity, and then we're going to perhaps address it in the most simple way, which will be the use of robust standard errors. We will then move on, and we will also illustrate two different versions of the weighted least squares regression technique, which is technically a generalized least squares method, but very similar to ordinary least squares, in which the model is weighted with respect to whatever our assumed source of the heteroskedasticity is. So I'm going to take you through those examples, and then along the way, we'll have a little bit of discussion about each. So in my do file here, I am going to be using the wage one data that is found in the Boston College website, data that we have used routinely throughout the semester. And so I'm just going to run my do file up until this first part, very simple regression, where I'm just regressing an individual's wage on education experience, and then we also have an indicator for if that individual is female. So we run this model, and what we see when we run this model is all three of our right-hand side variables are statistically significant in this particular model. And the main variable of interest, which is education, we can see appears to have a marginal effect of about 0.60. Given that wage in this particular sample is an hourly wage, we can therefore infer that basically for every year of education, because in this sample education is counted off by years, 1, 2, 3, 4, so on and so forth. So for every additional year of education, someone's hourly wage rises by a little bit over 60 cents, but essentially 60 cents. And again, we can see that that is statistically significant. For every year of experience, we see an individual's wage rises by about 6 cents. And in our sample, female individuals on average are paid about $2.15 less than their male counterparts. This, of course, is holding education and experience constant. So one of the big concerns we have in this model is that there could be some heterogeneity that is leading to specifically heteroskedasticity. But we can test for that. The first thing we can do is we can just run an RV plot, and this will sort of help us visualize whether we have a heteroskedasticity problem. So in this particular RVP plot, we are going to check to see if there's any particular heteroskedasticity with respect to education. So we're just going to run this section. This actually is going to produce a graphic. Now, what we notice here is that when you look at education with respect to the residuals, and these are the residuals from that baseline model, we can see that as education increases, the residual spread seems to increase as well. And so what this means is that we could have a violation of our ordinary least squares assumption, and that therefore we have heteroskedasticity in this particular model. We can also, in addition to this visual test, we can run a white test, which will test for basically heteroskedasticity in my model at all. So this is specifically looking with respect to education. There's some evidence here that there's heteroskedasticity in our model with respect to education. We could check the other variables, or we could just run the white test. So we're going to run the white test here. And when we do that, we can see that these are the results. The white test null hypothesis is that there is no heteroskedasticity, or rather that we have homoskedasticity. We can see here that our p-value on that test is 0, meaning that we can reject the null hypothesis of homoskedasticity, and this would certainly imply that there is a non-negligible amount of heteroskedasticity somewhere in our model. We don't exactly know where or even kind of necessarily how to model it, but we do see that it's there. So once we have identified that we have heteroskedasticity, we want to take steps to identify it. Now, in this particular video, I'm going to focus on non-specification ways that we can deal with the heteroskedasticity. If we think there's heteroskedasticity, one of the things that we want to sort of, maybe even the first thing we want to consider is respecifying our model. Perhaps checking nonlinearities, checking for interesting interactions. That can sometimes also account for and deal with the particular heteroskedasticity. In this particular video, we're specifically going to just focus on ways that we can alter the regression in a way that deals with the heteroskedasticity without changing the actual specification. So throughout, we're going to maintain the same model specification, regressing wage on education experience and an indicator for female, but we're going to alter the ways in which, the assumptions rather, that we make with respect to our models. So the second thing, or I'm sorry, the first thing that we can do to address heteroskedasticity is we can simply run our models with robust standard errors. And so to do that, we take, again, the same specification as before, and we add VCE, open parentheses, robust, close parentheses. And when we run this model, we can see that there are no changes to our coefficient estimates, but we do get some changes to our t statistics, which suggests that the robust standard errors are larger than their non-robust counterparts, which is precisely what we would tend to expect. Now, oftentimes one of the things that students do here is they say, okay, well, I looked at robust standard errors. My coefficient estimates didn't change. I have slightly lower t statistics, but I haven't actually lost statistical significance in any meaningful way. And so that's fine. Okay, then I've dealt with the heteroskedasticity problem and I can move on. And that's unfortunately not necessarily the case. The reason why the use of robust standard errors may not necessarily capture the full effect of heteroskedasticity in our particular model is because, again, our heteroskedasticity may be coming from something that is going beyond that which can be solved with robust standard errors or even cluster standard errors. Here we're just doing robust standard errors. We could also do cluster standard errors if we wanted to, but it's not really the point we want to make. So the next step is we can run what we call weighted least squares. And here we can make assumptions about where we think the heteroskedasticity is coming from. So again, we're going to assume here that the heteroskedasticity is coming from education. And if we think heteroskedasticity is coming from education, then what we want to do is we want to weight our initial specification with respect to basically the inverse square of education. So we first want to create a variable, education underscore weight, and the value of that is going to be equal to 1 divided by education, so the inverse of education squared. Now, if you think about this, at first it can seem bizarre to you why this matters. But remember that the nature of heteroskedasticity here, and if we think it's coming from education, means that as we increase education, the residuals that are being computed from our ordinary least squares regression are the distribution of them is changing as we increase X. And again, if we go back to the RVP plot as we saw before, it certainly seems like as education increases, the spread of our error terms is also increasing. However, one thing I will point out, and we'll just go back to the RVP plot again. If you look, indeed, it seems like the spread is larger, but perhaps the distribution itself is still relatively and normally distributed, right? That would be the hope, although, of course, we certainly have some questions about that just by looking at this particular plot. So what we do is we create this weight again, 1 over education squared. And then what we do is we just tack on to the end of our regression this little bit of code. What this code does is it puts in an analytical weight into our model. And that analytical weight, of course, as we previously had generated, is based upon the square of the inverse of the variable that we think is causing the heteroskedasticity. So in other words, our regression is now going to be run, and basically we are going to weight the regression estimates with respect to the inverse of education to account for the potential heteroskedasticity that we think might be coming from education. So we run these 2 little lines of code. Okay, now when we run the model, we can see that our coefficient estimate on education is still significant, but we do notice it's a little bit smaller. Previously, we were estimating about a 60-cent per hour effect coming from every additional year of education. Now we're at about 48, 49 cents for every year of education. So if we again think that heteroskedasticity is just coming from education, and again, as researchers, we are specifying and we are modeling these decisions, then we would tend to believe these results a little bit more. Now, ultimately, maybe you don't think 60 cents versus 48 cents or 49 cents is that much of a difference. But again, in regression analysis and in causal inference, we're trying to estimate population marginal effects by using samples. And so the question you have to ask yourself is if I think there is heteroskedasticity coming from education, what does that mean? What it means is that the nature of education as one increases, that the fundamental relationship between education and someone's wage is changing. In other words, that education increases, the nature of that relationship is evolving. Now, one way that we can deal with this, as I previously mentioned, is we could look for nonlinearities. So we could test our model and we could, for example, include a square of education on the right-hand side, or we could look at the log of wage on the left-hand side. And these could potentially deal with, again, that heteroskedasticity problem. One thing that those things do not do, nor does the regression results you're looking at here, is generally deal with the issue of heteroskedasticity potentially showing up in any of my right-hand side variables. As we saw previously, if we go back and look at our white test, we had extremely strong evidence of heteroskedasticity. When we looked at the robust standard errors model, however, it didn't seem like the heteroskedasticity was so bad that it was causing any coefficient estimate changes. However, when we applied the analytic weight, specifically assuming that education was the source of the heteroskedasticity, we did see a small reduction in the effect of education, again, believing this is potentially the more precise measure. Lastly, what we're going to do is we're going to do some statistical hoop jumping through, and we're going to create now a more generalized weighted least squares model, meaning that we're not going to assume we know precisely where the heteroskedasticity is coming from. We're simply going to assume that somewhere in my model there is heteroskedasticity. And then what we're going to do is we're going to use estimation of the original baseline model, and then estimation of some additional components such as the standard errors, And we're going to use that to create analytic weights that will take all of the variables on the right-hand side into consideration and give us a much more generalized weighted least squares outcome. So the first step is to just run the baseline regression. Again, this is the same specification that we've seen from the beginning. The second bit of code here, predict fit, is basically going to save the results of that initial model, and we're going to name it fit. Then we're going to save the residuals from that baseline regression, and we're going to name them SE, or for standard error. Okay. In this third step, what we do is we take the absolute values of standard errors. And again, this is a fairly important component of the weighted least squares approach. Ultimately, we are going to use the absolute value of the standard errors. And again, these are standard errors which are generated from the baseline regression. So the way that weighted least squares works in this scenario is we take the residuals from the baseline model, which again, by running weighted least squares, we are making the statistical decision that we have heteroskedasticity. So we take the heteroskedastic standard errors from the baseline model. We're then going to take the absolute value of them, and then we actually regress the estimates generated from the initial baseline, which was, again, we named fit, and we're going to run a regression where we take the absolute value of standard error and we regress that on the estimates from our initial model. Basically, what we're going to do is we're going to measure the effect of the estimates in our baseline model on the absolute value of the standard error. We're going to take those results from that regression. We're going to call them fit2. So now we have a second fitted model, which we're going to call fit2. What we're then going to do is we're going to generate the analytic weight from those results. And when we do that, again, much like education previously, we're going to take the square of the inverse of the values there. And then we just drop it in as an analytic weight. So we generate the weight as weight equals. And then for the weighted least squares regression, we drop in the analytic weight just as we did before. And so again, the idea is that we estimate a model for which we are making an assumption that there's heteroskedasticity. We take the results, we save those estimates, call them fit. We then take the standard errors from those estimates, save them, call them SE. We then take the absolute value of the standard errors, and then we run a regression where we look at the absolute value standard errors regressed upon the initial outcomes. And I think about what this means. It basically is testing the sensitivity of the standard errors to the regression results from the baseline model. It's sort of like reverse engineering in a way the heteroskedasticity issue. That if we think there's a heteroskedasticity problem, what does heteroskedasticity do? It causes the standard errors that are estimated from the ordinary least squares regression to not model the actual behavior that we see in the data. Again, our assumption of ordinary least square standard errors is that they are normally distributed and have no relationship with the right-hand side variables. Here, we are assuming that the standard errors have some relationship with the right-hand side variables. We're essentially estimating that relationship with this particular regression. We're taking the results of that relationship and we're using it to fit the analytic weights for our weighted least squares regression. So what this regression does is it estimates a weighted least squares model in a very general way, trying to, in a sense, reverse engineer the heteroskedasticity problem. So we're going to run all of this code. And when we do this, what we notice is that now the effect on education is considerably smaller, 20 cents less than the previous weighted least squares model, which had about a 49-cent effect. Now we're estimating about a 27-cent effect. Now, this is a model, again, in which we are acknowledging we don't think we necessarily know where the heteroskedasticity is coming from. So the weighted least squares approach here is careful, and that's ultimately one of the reasons why we see the effect on education is even smaller than before. But again, what this model does is it gives me a couple bits of information. First off, even after accounting for heteroskedasticity in several ways, I see that education still is causally related to wage in both a positive as well as economically meaningful way. If we think back to the baseline approach, we started with about a 60-cent effect of education on wage every year of education on hourly wage. We then moved on to robust standard errors. We saw no effect on the coefficient, just slightly smaller t-statistics. We moved to a weighted least squares approach where we made the assumption that education was the sole source of heteroskedasticity. We used the square of the inverse of education to create an analytic weight. I got about a 48-cent on the dollar, 48-cent effect coming from education for every year of education. And then in this last model, what we've done is we've basically said we don't know where the heteroskedasticity is necessarily coming from. We just think it exists. It could be coming from wage education or experience, or it could be coming from all three. What we're going to do is we're basically going to estimate the underlying relationship between our standard errors and our baseline regression results. We're going to use that to create analytic weights that will more naturally account for the unknown sources of heteroskedasticity in our particular model. And when we do this, again, we get an effect of about 28 cents for every year of education in terms of someone's hourly wage. You'll notice, and if we just sort of scroll up here, that the other effects are very close to being the same. So experience is close to where it is modeled in the original baseline model, and we can see that female is not that far off as well. So there are somewhat changes for experience in female. All of the directional coefficients are the same, so no signs are flipping here. So the question sort of becomes, well, what does this all mean? And in the context of research, what is it that we should report? So if we go back to the do file, you'll notice that we have this output command here at the end. I'll just make this so you can see all of it. So this is going to take in the do file where there's these EST-STO. This is storing the regression results so that we can make a nice table with them. And then in this final line of code, this is us actually creating the table. What you can do is you can also add the title to the table in this particular way, and you can label the actual models, and you'll see this here in just a moment when you actually sort of look at the output. I'll make this do file available, of course, so you don't have to remember any of this. Okay, so let us run this last bit of code, and then let's check out our table, our nice, beautifully made table. Okay, so we've run that last bit of code and we click on it. Okay, so we have four models: the baseline, ordinary least squares with robust standard errors, and then our two weighted least squares models. Again, the third one here is we're only accounting for heteroskedasticity coming from education and nowhere else. And in this final model, we're assuming that we don't know where the heteroskedasticity is coming from, so we're sort of just generally going to weight our model by a fairly seemingly complicated process of estimating the actual relationship between our error terms and our baseline regression results. And so this is the sort of literal top line result here that we're interested in. And so from a researcher's perspective, here's basically what I would say. When you check the effect of education on someone's hourly wage and just the baseline ordinary least squares, we get about a 60-cent per hour effect. Every year of education increases somebody's wage by about 60 cents. The checking for robust standard errors doesn't change this result at all. It doesn't reduce the statistical significance at all. Again, we have about a 60-cent per hour effect. In the third model, where we make note that heteroskedasticity is coming from education, we see now about a 49-cent per hour effect. What that probably means is that there is some heteroskedasticity coming from education. Once that is directly accounted for, we do get a slightly smaller effect on education. which makes a lot of sense. And then the fourth model, where we do a very general approach to the weighted least squares model. And again, we don't necessarily make a fundamental statement about where the heteroskedasticity is coming from. We're sort of just saying it exists in our baseline model. So let's account for it and be very safe. And when we do that, we can see that the effect falls to about 28 cents. So as a researcher, I'm basically created for myself, if you will, a confidence interval. Basically, I would say that the effect of education on wage is probably around 50 cents to 25 cents per hour. I come up with that because I don't necessarily think that the effect is 60 cents. The reason why I don't think it is that once I deal with just the heteroskedasticity coming from education, I see that is considerably lower at 48 cents. So I'm basically allowing for the potential that somewhat under reports or the effect. And so we started sort of 50 cents on the dollar. And then I'm using this second weighted least squares model to create the sort of bottom threshold, the bottom part of that confidence interval. So I would say that, in my model, after accounting for unknown sources of heteroskedasticity, that the effect of wage on, rather the effect of education on wage is about, for every 1 year of education, wage rises from about 50 cents to about 25 cents, with, of course, individual outcomes being particularly unique.